In this lesson, we're going to talk about representations of functions as power series. So first it says recall the following equation. So we have this equation where it says 1 over 1 minus x equals, and then we have 1 plus x squared plus x cubed, and so on. And this whole thing equals sigma and starts at 0, goes to infinity of x to the n. And then over here it says the absolute value of x is less than 1. So you're probably noticing this looks familiar. And it says right here, it's an infinite geometric series where your first term is 1, and then your r value or your common ratio is equal to x. So we're used to seeing this in this direction where you're given your geometric series. When you start by plugging in 0 for n, you get 1. Then you plug in 1, you get x. When you plug in 2 for n, you get x squared, and so on. And then in order to find the sum, we're using the formula a1 over 1 minus r. So again, a1 is this first term, so you have 1 over, and then 1 minus, and then r is x. So therefore your series is equal to this sum. So in this lesson, what we're going to do is we're going to take functions that are of this form, 1 over 1 minus x, and we're going to rewrite it in a power series form where we have x to the n. So here we have a diagram. It's a geometric illustration of the above equation. And so right here in blue is our function for f. And then it says, because the sum of a series is the limit of the sequence of the partial sums. So here's the sum of the series, and it's equal to the limit as n goes to infinity of the partial sum. And then it says where s of n of x is equal to 1 plus x squared, all the way to x to the n. And it says, notice that as n increases, the nth partial sum s of n of x becomes a better approximation to the function f of x in the interval from -1 to 1. So one more time, here's your function f. Here's your graph for s sub 2. So again, that would be the partial sum taken out to 1 plus x squared. Then we have s sub 5, s sub 8, s sub 11. And again, as n increases, you'll notice that this curve is more closely resembling the original curve of f in the interval from -1 to 1. This example says express the given function as the sum of a power series and then find the interval of convergence. So when the function is of the form 1 over 1 minus x, we can rewrite this function in a power series form, x to the n. So when it's 1 minus something, we take that thing and we raise it to the power n. So right now our function's not quite in the right form yet. So to get it into the right form, in the denominator, we just need it to say 1 minus something. So instead of 1 plus 9x squared, we're going to rewrite it as 1 minus negative 9x squared, where this negative is equivalent to a positive. So now it's in the right form because it's 1 over 1 minus, and then this is our x term. So again, using the equation from above, we can rewrite this function using sigma, n starts at 0, goes to infinity. And then this right here, this negative 9x squared, we take it and we put it right here, so it says negative 9x squared, and we raise it to the power of n. So we could leave our answer like this, or because we have this -1 raised to the power of n, we can pull that to the front. So we have the series -1 to the n, and then 9x squared to the n. Okay, so I just want to recap. We took this rational function, and we put it in the form of 1 over 1 minus x. And this is equal to the sigma notation, where we take this -9x squared, and we raise it to the power of n. And then you could leave your answer like this, or I just chose to rewrite it like this so we could see that alternating part. So this function equals this series. And I just want to look at this series really quickly. If we were to expand it out, we'd start by plugging in 0 for n, so that would be 1. And then we'd plug in 1 for n, so that would make the next term negative. And when you plug 1 for n, you get 9x squared. Next, we'd plug in 2 for n, so this would be positive. When we plug in 2 right here, this would make 81x to the 4th. And then the series would continue to alternate. So this original function is equivalent to this series, which is written out 1 minus 9x squared plus 81x to the 4th minus, and then so on. And it's kind of cool that we just took a rational function and we rewrote it so that it's equal to an infinite geometric series. All right, so next we're going to identify the interval of convergence for this series. To do so, I want to look at the series in this form right here. You can really see the geometric series. It starts at n equals 0, and then your r value is the part that's being raised to the variable exponent of n. And remember, for an infinite geometric series to converge, that means your absolute value of r is less than 1. And I wrote that out because this is a geometric series. It converges when, and I took the absolute value of r, so we have the absolute value of -9x squared, and we set it less than 1. So since we have a product right here, we can take the absolute value of -9, which is just 9, and we can divide that to the other side of the inequality. So we get x squared is less than 1/9. So then we have the absolute value of x is less than 1/3. So therefore our interval of convergence is -1/3 to +1/3, not inclusive. For part B, we have f of x equals x cubed over x plus 2. So what we're trying to do is we're trying to get this function in the form of 1 over 1 minus x. So we have a little bit of manipulating to do. So first thing I want to do is I want to bring this x cubed to the front. So I'm just taking the x cubed and multiplying it to the front of the fraction. So that would leave 1 over, and then I'm going to rewrite this so that it says 2 plus x. Again, we're trying to get this fraction in the form of 1 over 1 minus x. So to do that, we're going to take this 2 and factor it out. So when we factor 2 out of both of these terms, it leaves 1 plus and then x divided by 2. So I just want to double check. 2 times 1 makes 2, and 2 times x over 2 makes x. So that works out great. Next, I'm going to move this 2 so that it's under the x cubed. And then we have 1 plus x over 2. So instead of 1 plus x over 2, we're going to rewrite that as 1 minus negative x over 2. All right, so we finally have this in the right format. It's 1 over 1 minus, and then we have this negative x over 2. So since this is in the right form, we're going to rewrite it using sigma, and we take this entire expression, negative x over 2, and we raise it to the power of n. So here's our series. So we can leave our answer like this, but just in case a problem like this comes up in a multiple choice problem and the answer is not written exactly like this, I want to show another way it could be written. So I'm going to rewrite sigma, and because we have this negative, I'm going to put the -1 to the n in front. So then we would have x to the n divided by 2 to the n. But we could also bring these terms back in, and when you do that, you'll get x to the n plus 3, and then in the denominator, you'd get 2 to the n plus 1. Because if you have same bases and you're multiplying, then you add their exponents. And then for the interval of convergence, we're going to use the series in this form because we have this negative x over 2 to the n. So this will be our value for r. And in order for this geometric series to converge, we take the absolute value of r and we set it less than 1. So because this is an absolute value, that takes care of this negative, and then we can also bring this 2 out. And then next we times both sides by 2. So we get the absolute value of x is less than 2. So our interval of convergence for our geometric series is going to be -2 to +2, not inclusive. For part C, we have f of x equals 7x minus 1, all divided by 3x squared plus 2x minus 1. So since our function is definitely not in the form of 1 over 1 minus x, what we're going to do is we're going to do partial fraction decomposition. So we take this original function and the denominator factors to 3x minus 1 times x plus 1, and we take both of these factors and we write two fractions. They're both linear denominators, so then the numerators are going to be constant values. So I just used a and b. At this point, we take this entire equation and we multiply both sides by the 3x minus 1 times x plus 1. When we multiply the side of the equation by this expression, that denominator cancels out and we're just left with 7x minus 1. When we multiply this side of the equation by this whole expression, you end up getting a times the quantity x plus 1, so that becomes ax plus a. Then you get b times this quantity right here, so we have 3bx minus b. So at this point, we set up our system of two equations with two variables. On this side, we have two terms with x, so we set the a plus 3b equal to the coefficient of x on this side. So I have a plus 3b equals 7. Then we take a and negative b, the two constant values, and we set it equal to the constant on this side. So we have a minus b equals -1. To solve the system, I multiplied this bottom equation by 3, and you can see that right here. And it works out great. The b's cancel out. You get 4a equals 4, so a is equal to 1. And then I plug this 1 for a back into this bottom equation, so we have 1 minus b equals -1. And then when you solve it, you get b equals 2. So I took a equals 1 and b equals 2 and plugged them into our fractions, and now we have f of x equals 1 over 3x minus 1 plus 2 over x plus 1. So now we're going to take both of these fractions and we're going to put them into the form 1 over 1 minus x. So for this first fraction, I'm going to rewrite this as -1 plus 3, and then at the same time, I'm going to factor out a negative. So let's make sure I did that correctly. Negative times 1 is -1. And negative times -3x makes positive 3x. Over here, I'm going to rewrite this denominator. So instead of 1 plus x, I wrote 1 minus -x. And now we're ready to rewrite both of these in sigma notation. So we have 1 over 1 minus and then 3x. So 3x is what we're going to put inside the sigma and raise it to the power of n. And then I'm also going to bring this negative and move it in right there. And then we're going to do the same with this. I'm just going to leave this 2 on the inside of sigma. And this says 1 minus and then negative x. So negative x is what we're going to raise to the power of n. Okay, so we're just going to manipulate these a little bit more. What I want to do is I want to separate this x to the n for both expressions. And then also because both of these sigmas start with n equals 0 and go to infinity, we can rewrite this as one big sigma. So for this first expression, I'm going to write it as negative and then 3 to the n, x to the n. And then for this next expression, we're going to go plus 2 times negative 1 to the n, x to the n. All right, guys, stay with me. We're almost there. So finally, what we're going to do is we're going to take this x to the n and this x to the n, and we're essentially going to factor it out. And at the same time, I'm going to switch the order of these. So we have 2, negative 1 to the n, minus 3 to the n. And then again, we take this x to the n and we move it to the outside. All right, and here's our final answer. Next, we're going to identify our interval of convergence. So I want to look back right here because this is where we have 3x to the n and negative x to the n. So you can conveniently see the values for r. So first we have r equals 3x. So we do the absolute value of r and we set it less than 1. The absolute value of 3 is just 3. So I'm going to divide that over. And then we end up getting the absolute value of x is less than 1/3. Next we have right here r is equal to negative x. So we take the absolute value of negative x and we set it less than 1. So you get the absolute value of x is less than 1. Okay, so I tried to give us a little mini visual here. Kind of a sad attempt, but anyways, hopefully it helps a little bit. Here we have, again, the interval from negative 1/3 to positive 1/3. And then here we have the interval from negative 1 to positive 1. So when you have a sum of two series like we had up here, to find the interval of convergence for the entire sum, what you do is you take their intersection. Or another way to think of it would be where the two intervals overlap. So their intersection, or where they overlap, ends up being from negative 1/3 to positive 1/3. So our interval of convergence for our series is going to be negative 1/3 to positive 1/3, not inclusive. All right, guys, thanks so much for watching, and please subscribe to my YouTube channel, Math with Yosh.